Hello and welcome. In this video, I'm just going to show my particle in a box simulation in MATLAB that I made I think it was like before my third semester of graduate school or something, but yeah, it's pretty cool. Alright, so we could arrange the particles in any geometry, but let's arrange them into an octahedron, and we'll connect the middle particle to the rest, and we'll see what happens. So basically, we could connect each particle and to one another. So for example, particle 6 could be connected to 1, 3, 5, 2, 4, or 7. Or sorry, 1, 2, 3, 4, 5, 7. There we go. That's a more systematic way of saying it. But we're gonna, I don't know, we're gonna say that the spring constant is 1,000 newtons per meter. The equilibrium length is going to be 1.01 actually. In this diagram it says 2, but I put it to 1.01 meters. Then we're not finished, so we type in a 0. We have default connections. The default connections are 1 connected to 2, which is connected to 3, 4, 5, 6, and, a chain of connections, but we're going to connect it a different way. And then we'll type 1 when we're finished. So in this program, you could set the initial velocities and positions. So I set the initial velocity of particle 6 to 100, 100 meters per second for the x, y, and z directions for particle 6. But then for the rest of the particles, I inputted the 0 vector, meters per second, and I ran the simulation for 10 seconds using ODE 45 with intervals of 0.01 seconds. So additionally, the particles are repelled by one another and by the walls of this virtual box. So the repulsion between the particles are encoded in what I call the repulsion matrices. So there's one matrix for each of these sets of repulsions. So here's the resulting particle simulation for 10 seconds. And as you can see, it's kind of like bouncing from one corner to the other. It's just focusing on bouncing between those two corners. It's pretty cool. It kind of just like goes like this, sort of. Yeah, pretty cool. But we could do any geometry or arrangement or any initial velocities, any kind of repulsions or number of particles, whatever. I made the simulation pretty general, so we could input all those values. So here are the plots of the x, y, and z positions as a function of time. As you can see, they're kind of like they're kind of sinusoidal with some like smaller sinusoids embedded within this larger sinusoidal pattern for each of the x, y, and z coordinates, which is also pretty cool. That's the word I use to describe everything pretty much, but it's a good description. Alright, so that is it, and thank you for watching.